Welcome! Today, we're kicking off a two-part deep dive into the incredible cellular physiology of the inner ear. First up, we're exploring the endolymphatic potential and the stria vascularis, which is basically the power source for your hearing.
Right, so in this explainer, we're going to tackle that power source. Then, in part 2, we'll get into what happens when things go wrong with the molecular basis of ototoxicity and aging. But first things first, let's understand how this whole system gets its juice.
I know, it sounds a little strange, right? A battery in your ear? But the answer to this question is the absolute key to understanding how we can hear with such breathtaking sensitivity. We're talking about sounds that move our eardrum less than the diameter of a single atom. It's incredible.
Okay, so let's get into the why. We'll start with the charge of this battery itself. And you have to understand, this isn't some minor electrical quirk, it's a feature that is truly one of a kind in all of human physiology.
So what are we talking about? The special fluid that fills the hearing part of your inner ear, it's called endolymph, carries this really powerful positive charge. We're talking about plus 80, sometimes up to plus 100 millivolts. To put that in perspective, that is the highest positive voltage found anywhere outside of a cell in your entire body.
And the official name for this charge is the endocochlear potential, or EP for short. I'm telling you, without this potential, our sensitive hearing would be completely impossible. It is the fundamental energy source for the whole process.
Now here's where it gets really cool. You've got this plus 80 millivolts in the fluid outside the sensory hair cells. But inside those cells, they have a typical negative charge, around minus 70 millivolts. So what happens when you put them together? You create this enormous 150 millivolt driving force across the cell. It's like having a massive amount of electrical pressure ready to go. And that's what powers the amplification of even the quietest sounds. It's the ear's secret weapon.
So, the big question is, how on earth does the body build up and maintain such an extraordinary electrical charge? Well, for that, we need to take a look at the cochlea's own dedicated power plant.
And here is the generator. It's a highly specialized three-layered structure called the stria vascularis. You should really think of it like a tiny biological factory. You've got the marginal cells on the assembly line, and their whole job is to actively pump potassium ions out. Then you have the intermediate cells, which are actually related to the cells that give your skin its color, and they're crucial for managing the flow of those ions. And finally, the basal cells act like the factory's walls, forming a tight electrical seal, so none of that precious charge can leak out.
Okay, so let's zoom in even further. We're going from the factory floor right down to the specific little machines, the molecules, that make this whole system go.
Potassium is the absolute star of the show here. When a sound hits your ear, potassium ions, that's K+, rush into the hair cells. That's what creates the nerve signal. But you can't just let that potassium build up. So the body has this incredibly efficient recycling system that grabs those used ions and shuttles them all the way back to the stria vascularis power plant, getting them ready to be pumped out for the very next sound. It's a perfect loop.
So how does the power plant get its raw materials in the first place? Well, that's where this key player comes in, the NKCC1 co-transporter. You can literally think of it as the charging port for the whole battery. It sits there on the marginal cells and actively yanks sodium, potassium, and chloride ions right out of the blood supply to fuel the system.
So if NKCC1 is the charging port that brings the energy in, then this channel, KCNQ1/KCNE1, is the power outlet. Once all the ions are loaded up inside the stria, this is the final valve that precisely lets a stream of potassium flow out into the endolymph, and that's what creates and maintains that powerful plus 80 millivolt potential we keep talking about.
Okay, we've got this beautiful, elegant, and really powerful biological battery. So what happens if we mess with it? What happens if we just pull the plug?
And that brings us to a really important clinical pearl. By the way, if you're enjoying these kinds of deep dives, please take a second to like and subscribe for more custom medical videos just like this one. Okay, so moving on. Because the stria vascularis is such a high-energy system, constantly burning fuel, it's incredibly sensitive to anything that disrupts it, and that makes it a prime target for certain drugs.
And here's where this gets super relevant in the real world. A very common class of drugs called loop diuretics. You probably know of furosemide or Lasix. What do? They directly target and block that NKCC1 charging part we just talked about. So you can see here, on the right, it basically just jams the port, stopping the stria from loading up on the ions it desperately needs to power the battery.
And the effect is, well, it's not subtle. It happens almost immediately. As you can see in this chart, the endocochlear potential completely collapses, It plummets from a healthy plus 80 millivolts all the way down to almost zero. And without that electrical driving force, the ear's amplifier just shuts down, causing a sudden, the thankfully usually reversible, hearing loss.
Whew, okay, that was a lot of pretty intense cellular physiology. So let's just pull back for a second and quickly summarize the absolute most important points from this explainer.
So here's what you really need to remember. First, your inner ear has a powerful plus 80 millivolt battery called the endocochlear potential. Second, that battery is constantly being charged by a 3-layered power plant called the stria vascularis. Third, the key machinery doing the work is the NKCC1 charging port and the KCNQ1 power outlet. And finally, you can actually unplug this whole system with common drugs like furosemide, which block that charging port and cause the potential to collapse.
And this leaves us with a final and pretty profound thought to chew on. The stria vascularis has one of the highest rates of blood flow and metabolic activity in the entire body. It's working that hard. So, if a common drug can so easily and so quickly shut it down, what does that tell us about the delicate high-energy balancing act that's required just for us to perceive the world? We'll explore that fragility a lot more in Part 2. Thanks for joining me.
Now, continuing from our discussion on the inner ear, let's dive right into the molecular basis of ototoxicity and aging. We're going to explore what happens when the ear's most sensitive cells really come under attack.
It's a great question, isn't it? What could possibly link these two things together? Well, the answer is they can both lead to hearing loss. And here's the kicker. They do it by targeting the exact same exquisitely sensitive structures in our inner ear. Okay, let's unpack this.
So, to really get a grip on hearing loss, you first need to meet the star of our show, the outer hair cell, or OHC. Now, these aren't just passive little sensors. Oh no. They are the biological engines that literally power the incredible sensitivity of our hearing.
And when these crucial OHCs get damaged or die off, what you get is sensory neural hearing loss. This is, by far, the most common type of permanent hearing loss, and today we're zoning in on two of its biggest causes: a direct chemical assault and a slow, steady siege of time.
The power of these tiny cells is it's astonishing. The OHCs work together to form what we call a cochlear amplifier, and they provide this incredible 40 to 60 decibel boost to sound. So when you lose them, you don't just lose volume. Sounds become way less clear, because that critical amplification is just gone.
So how do we lose these cells in the first place? Well, let's bring in our first antagonist, a class of drugs we call ototoxins. These are medications that, while often totally life-saving, can unfortunately act like a poison to the cells of the inner ear. And here's exactly how they do their dirty work. Whether we're talking about an aminoglycoside antibiotic or a chemo drug like cisplatin, the process is the same. The drug gets inside the hair cell, and once it's in there, it starts churning out these highly destructive molecules called reactive oxygen species, or just ROS. This creates this intense oxidative stress that completely overwhelms the cell's defenses. It damages all the important stuff inside and basically triggers a self-destruct sequence called apoptosis. The cell is programmed to kill itself.
Now, what's really fascinating is that this attack isn't random. Nope. These drugs have a specific target: the outer hair cells located right at the beginning of the cochlea, in what's called the basal turn. And since that part of the cochlea is responsible for processing high-frequency sounds, the damage results in that classic, progressive, and sadly irreversible high-frequency hearing loss.
Okay, let's switch gears and talk about our second antagonist. This one isn't a chemical you take, it's just time itself. We're talking about age-related hearing loss, or, as it's medically known, Presbycusis. I love this quote because it just perfectly captures the whole issue. Think about it. That same basal turn we were just talking about, the one that handles high-frequency sounds, it's the metabolic hotspot of the entire inner ear. It is constantly working, burning through massive amounts of energy and oxygen 24/7 for your entire life.
You know, all that relentless work over decades, it comes at a cost. It creates a state of cumulative oxidative stress. It's essentially a slow, gradual burnout. And it just makes sense, right? The hardest working cells are going to be the first to wear out and fail, which is exactly why we see that characteristic high-frequency hearing loss as we get older.
So on one hand, we have this acute, brutal chemical assault from drugs, and on the other, a slow, chronic siege from aging. They seem like completely different things, but what if they're actually attacking the very same weakness? How do these two stories connect?
Okay, this table right here. This is the big aha moment of this whole explainer.
Just look at the parallels. Both ototoxicity and presbycusis target the outer hair cells. Both of them hit the basal turn of the cochlea. Both involve oxidative stress that leads to cell death. And guess what? Both produce the exact same pattern on a hearing test, a high-frequency ski slope loss. It's incredible. Two completely different paths converge on the very same fundamental vulnerability, the super high-strung, metabolically active nature of our high-frequency hair cells.
And you know, figuring this out isn't just some academic puzzle. It has huge clinical implications. This is why we have to so carefully monitor patients who are on ototoxic drugs, often using special high-frequency tests. But even more exciting, it gives researchers a common enemy to target, that oxidative stress, in the race to find future therapies to protect and even restore our hearing.
And that leaves us with this final, really provocative thought. If both of these destructive pathways share a common mechanism, could a single solution protect us from both? I mean, could therapies that fight oxidative stress, or maybe even futuristic gene therapies like ATOL1 that can regenerate lost hair cells, could they one day silence the damage from both life-saving drugs and the simple passage of time?
And for your clinical pearl, remember to stay curious, because really understanding these molecular pathways is always the very first step to conquering them. Thanks for watching, and if you found this helpful, please like and subscribe for more custom medical explainers made just for you.